Hi, Boby.
Hi, Aniruddhan.
So this week we need to
Do something more.
right? We should learn some circuit techniques and circuit theorems actually, right? So it can be proven. We are not going to do the proof, but there actually there are circuit theorems which help you solve circuits more easily.
Compared to the mesh equations.
Compared to the mesh equations, node equations and so on. In specific situations, we'll learn to use them.
Okay.
Okay, so maybe we'll start with a simple example.
That will be helpful. Yeah.
Okay, so suppose I want to I have a voltage source and I want to create a smaller voltage from that, right?
Yeah.
We need to come up with some. It may not work very well, but we want it to work, right?
So if you want to reduce the voltage, I can put two resistors in series and then take the output voltage.
Take the output voltage. So maybe we'll just draw that.
Okay.
So let us say let's take some voltage. Let us say I start with 15 volts.
Yeah.
Okay. So
15 volts and I want let's say 10 volts.
10 volts. Okay, perfect. And we'll go back to DC.
Yeah.
Right?
Just to start, that's better.
To start, we'll understand it with DC and then see if it works for AC.
Yes.
So we start with 15 volts and you said use a resistive divider, right?
Yeah.
So I will do that. So what I will do, I will show like this. So we wanted 10 volts.
Yeah.
So this we wanted to be 10 volts. So I need 2/3 of the voltage. So we need two resistors. So let's say I'll call this R2 and R1.
Yeah.
We know that R2 by R1 plus R2, right?
Yeah.
Because the same current flows through them. We have seen this last term.
That has to be 10 by 50.
This has to be 10 by 50. This is what we can tell. The value of R1 and R2, as long as the ratio is like this, it seems like the value can be anything, right? We may want to use very small current flowing through R1 R2, so you can choose R1 and R2 in kilo ohms if you want.
Okay.
Right? So maybe what I will do, I am going to say R2 is 10 kilo ohms. Okay. And R1 is 5 kilo ohms.
Yeah.
Then I will get 10 by 50.
Correct.
Perfect.
Yeah.
Right?
Yeah.
So we'll just use these two sets of numbers.
So there will be always 1 milliampere going through.
There will be 1 milliampere flowing through like this.
So there is always some loss.
There is always some loss.
One way to get it.
One way to get this.
Yeah.
But if I were to, something seems off.
What you are going to do with this voltage?
What are you going to do with this, right? So you need to use it somewhere. So most likely you are going to use it to maybe apply it across another resistor or something.
Okay.
Right? So if I am going to show that in blue color, so maybe
some load resistance.
Some load resistance RL, let us say. Right? But the minute you do this, this current is changing. Right? Originally we did not have that problem when you didn't have RL. Right? But now that current is going to change. Okay? Which means this is no longer 1 milliamp. This thing is no longer true. Right? With RL. No?
So if RL is changing,
yes.
Every time I have to write the equation.
You have to correct. Seems very cumbersome.
Not very friendly.
Not very correct.
Is there any better way?
There must be a better way, and it turns out there is. Okay. So this is one of the theorems we want to learn this week. So this theorem is called Thevenin's theorem.
Okay.
Or some people just say Thevenin theorem. So what it says is that if you take a very big network, so I have some network and it has some voltage sources, it has some current sources, let's say resistors. We said we'll start with DC voltage, let's just start with DC voltage, DC resistance, simple. So lots of voltage sources, lots of resistors
connected in some fashion.
connected in some fashion, any fashion, and let us say across some two nodes, let us say N1 and N2. These are two nodes inside the network. Like here we have taken across R2. We have taken out two nodes across R2.
Yeah.
So it is almost like this is N1 and this is N2. And you want to connect some load resistance or something like that. You want to use those two nodes to connect somewhere else. Then what this Thevenin's theorem says is that you can replace the entire network by a very simple equivalent.
We can represent.
You can represent. So you can across those same two nodes, no?
N1
and N2. You can replace the entire network by a combination of exactly two components. One is a voltage source. We'll call that the Thevenin voltage.
Okay.
The other one is a resistance, which we'll call the Thevenin resistance. And now you can use this model everywhere.
So if I mean this RL, then we can fit it across N1
yes,
and N2.
the idea is that now if you need to connect RL, so you can actually keep changing RL if you want. It is so easy to calculate. Instead of having 10 voltage sources and 100 resistors and calculating, you know, tens of mesh equations, node equations, etc., you have exactly one loop.
Okay. This is
Right?
very easy.
Very easy. So if you keep changing
It's applicable for any
number of voltage sources, any number of resistors, any connection between them, series, parallel, it doesn't matter. You can build a Thevenin model for all cases. And in fact, I will tell them now itself that you can have DC current sources. In fact, you can also have AC sources.
Okay.
So you can build Thevenin equivalents for AC networks as well.
Oh.
Okay. So
we will try in our example.
we should try for our example, right? So this is what we are saying. You are putting some load resistance. So there is a unique set of Thevenin resistance and Thevenin voltage.
Okay.
Okay. And now we can also see RL is changing. So VTH and RTH cannot be functions of the load resistance.
Correct.
Right?
Yeah.
It is representing this network N, right?
Yeah.
So this network N is being replaced by this. So this cannot be a function of RL because RL is outside the network.
Yeah.
So this VTH and RTH should somehow be values that are dependent on all the voltage sources and all the resistors. We'll do it for that simple network. We will get a lot of understanding.
Sure.
So let us take this case. So
the question is how to find out VTH and RTH.
VTH and RTH. So what we are saying now is that let us say I take this network. We said 5 kilo ohms, 10 kilo ohms. So across N1 and N2, we are now saying that this network is identical to this, right? So across N1 and N2. So we have some VTH and some RTH. Thevenin voltage, Thevenin resistance. This is identical, so you can connect anything across N1, N2. We just need to find out what these values are.
Okay.
Okay. So, and I'll also say that both V Thevenin is not a function of RL, right? R Thevenin is also not a function of RL.
Yeah.
So they have to be independent. They will depend on this 15 volts R1 and R2. And it is this VTH, RTH single value is valid for any RL. That is what also we are saying, right?
Yeah.
The theorem is saying the values will be independent of RL and you can connect any RL, it will be valid. We need to find an easy way.
So VTH basically voltage across the Thevenin equivalent circuit output voltage and then the voltage without load.
Without load, open circuit.
Both are same.
Both are the same. Correct. So in fact, that's what we should do. So since these two networks are completely equivalent, we need to apply some load, right? the two networks are equivalent.
Correct.
So the voltages across N1, N2, the current flowing from N1 to N2 through the load, they all should be equal in all of these cases, in both these networks.
Understood.
So that is an easy way to solve it.
Correct.
Right? So, well, you can use any RL you want.
Let us check for the extreme cases you
Extreme
mentioned.
cases, right?
RL infinite and RL 0.
Let us do that, right? So we will choose two cases, RL equal to infinity, and second case is RL equal to 0. Because it makes our calculation easier. We don't have to choose some random value of RL, right? Okay, we will do that. So let us say that we take this network first and we'll do open circuit.
Yeah.
Okay.
That means RL is removed.
RL is removed. So RL equal to infinity, right? And we are saying in that case as well, RL is removed. No RL.
Yeah.
And so if in this case it's easy, if there is no RL, current equal to 0.
Yeah.
So there is no voltage drop across the Thevenin resistance.
Yeah.
So this open circuit voltage clearly is equal to VThevenin. Right? There's no voltage drop across RThevenin. So all of this VThevenin will appear.
Correct.
As the open circuit voltage. Here in this case, we are not applying any RL.
Yeah.
So we need to find out the open circuit voltage, and that also we can
for
analyze. We design for anyways. You are right.
Yeah.
We design for 10 volts.
10 volts.
Right? We design for 10 volts. It is simply 10 by 10 plus 5 times 15.
Yeah.
So that is what we design. So clearly, in this situation, VThevenin is equal to 10 volts.
10 volts.
That is what we are saying. So simply analyzing the open circuit voltage directly gives us the Thevenin resistance. In fact, this is true for any network, right? Because in this side from the Thevenin equivalent circuit, so this is called the Thevenin equivalent circuit. So in the Thevenin equivalent circuit, it's very easy to see. The open circuit voltage is always the VTH. So that means if you, for a given network across two terminals, if you want to calculate the Thevenin equivalent, you should just calculate the open circuit voltage.
So
that will
open the load and
open
measure
the load
that voltage.
and measure the voltage, right? That will directly give you the Thevenin. In this case, it's 10 volts.
Yeah.
Okay. Let's try the other extreme case.
Okay.
We said RL equal to 0. So if you put RL equal to 0, what will happen to, so we need to do a short circuit.
Yeah.
So across node N1 and N2.
Yes.
And we need the same thing here. So we have VThevenin and RThevenin. And we are going to apply a short circuit here also. Okay. If you do a short circuit, it makes sense to find the current, no?
Correct.
Because voltage is clearly 0.
Correct.
The only thing you can find is the current.
Yeah.
I will call this the short circuit current. And it is clear that that is VTH by RTH. Right?
VTH we already know.
VTH we already know. So it is, what we need to find out is RTH.
Yeah.
Right? So it looks like RTH is nothing but VTH over the short circuit current. Right? Okay, okay. So, so RTH is basically the VTH over the short circuit current.
Yeah.
In fact, so that is basically the open circuit voltage by the short circuit current.
Yeah.
Right? That is what we are saying.
Correct.
And in this case also we can find out the short circuit current.
Yeah.
The short circuit current in this case is simply 15 volts. So 10 kilo ohms is bypassed. So it's 15 by 5.
Yeah.
That is simply 3 milliamperes.
Yeah.
So now we can, from this network, we saw that it is VTH by ISC. So the RThevenin is 10 volts by 3 milliamperes.
Yeah.
Okay. So this is basically 10 by 3 kilo ohms. 3.33 kilo ohms. Perfect. So which means now imagine I took my original network. I said that I want to connect 10 kilo ohms.
Yeah.
I want to see what the current is through that. I don't need to resolve the whole network. All I have to do is reuse the Thevenin equivalent network.
So across the N1 and N2 in the Thevenin equivalent circuit.
Correct.
Fit that resistor.
Fit
back.
that resistance.
Okay.
That's all. So, and now I can keep changing it. It's a very simple resistive divider every time. So, it's extremely simple. It's a one-step solution. The only thing is one time you solve for VTH and RTH. And after that you can change RL to anything. And you can find out everything about the network, about the load, not about the network, about the load.
Okay, okay. So should we find out how bad it was? I mean, initially we said there will be 10 volt.
Correct, you are right. So now with some load we need to find out, right? Correct, you are right. That's a good idea. So we expected 10 volts, no?
Yeah.
So we'll connect some resistance.
Yeah.
What resistance shall we connect? Why don't you pick
10K?
10K. Okay. And we want to actually find out what this voltage is.
Yeah.
We expected originally, we actually built this saying that we are going to get 10 volts. Correct? Okay. So let us see what we are going to get. So this is your load resistance.
It is a bit straightforward.
Still we will do it. So we will do it with the Thevenin. We'll do it with this.
Yeah.
We'll do it with the Thevenin equivalent. Show that both are equal.
Correct.
Right?
Perfect.
So this one, 10K and 10K is 5K.
Parallel, yeah.
So 5K, and now you'll get half the voltage.
Yeah.
Right? So you'll only get 7.5 volts.
Yes.
With this model.
Yeah.
Right? Solving the full thing. Is this correct?
Correct.
Okay. Now we'll also do the other case where we'll use Thevenin voltage gave us 10 volts and 10 by 3 kilo ohms.
Yeah.
And we are connecting 10 kilo ohms.
Yeah.
And this is VL. This is basically 10.
10 by 10 plus 10.
10 plus 10 by 3 times 10. Right?
Yeah.
So 30 plus 40. So 30 by 40 times 10. Right? So this is 3 by 4, 7.5 volts.
Yeah.
Perfect. So 30 plus 10 is 40. So denominator is 40. Numerator is 3 times 10, 30. 30 by 3 by 4 times 10. So this is 7.5 volts.
So it's matching.
It's matching, right? And you can keep doing this for every value, any load. So instead of 10 kilo ohms, you did 5 kilo ohms, you'll get the exact same answer.
Very useful.
So this is a very useful technique to simplify a very large network just once.
Particularly useful if voltage or current of one of the elements is required, that is varying.
That is correct. That is correct. That is correct.
Okay. This RTH, is there any other way of finding?
Okay. Yes, of course. So you can see, so let us go back to the Thevenin resistance model. So this is your, so we said this is VTH and RTH. So if I want to find out RTH,
that N1,
actually
N2 also
this is N1, N2, I'll mark that as well. So this is your Thevenin equivalent.
Yeah.
If I want to find out RTH, ideally what I should do is I should de-energize the voltage source
and
look from here and measure the resistance. I take an ohm meter and measure it.
Yeah.
I turn off the battery, measure it, I will find out.
So if it's a voltage source, I should just replace it with
short circuit.
Short circuit.
Correct.
Ideal voltage source.
Ideal voltage source. So what I do is I short circuit the Thevenin resistance, and the resistance looking in is R Thevenin.
Shall we try that for our circuit, whether we will get...
Correct. So we need to do that, right? Okay. So what we need to do then, for the full network also, across N1, N2, we do the same thing.
Yeah.
So what we can do, so this should be identical to, if you did the same thing for the network as well.
Yeah.
So we take this, right? And if you did, if you de-energize this 15 volt source,
we will show it as a
we'll show it as a short circuit.
Yeah.
Correct. So we'll instead of putting an X, we'll just show like this.
Yeah.
It's a short circuit.
Yeah.
Right. Here same thing. So it is a short circuit. Okay, so let us do this and see if we actually get RThevenin, what we calculated.
Yeah.
So what I am going to do, we need to find out the, we are going to short, right? So what you have is R1 in parallel with R2. So this impedance is R1 parallel R2.
Yeah.
Right? So this is basically 10 into 5 by 10 plus 5 kilo ohms, right?
Yeah.
So basically, is this correct? 10 kilo ohms in parallel with 5 kilo ohms.
Correct.
So 10 by 3, 50 by 15. So this is 10 by 3 kilo ohms. Perfect.
Same. Yeah.
Perfect, right? This was also 10 by 3 kilo ohms. Perfect. So if you need to find out the Thevenin resistance, then you can either do the short circuit current, which we did here, or even easier sometimes is to calculate, de-energize the voltage source like we have done here. We have made it a short circuit all voltage sources and just calculate the effective resistance across N1 and N2.
Okay.
Right? That also gives you the Thevenin resistance.
If we have current sources?
If you have current source, so then you need to open circuit. So you need to open current sources and short voltage sources.
Okay.
So
to find out RThevenin.
To find out RThevenin.
So remove the load first.
Remove the load first. Open circuit all
the voltage, all the current sources open circuit.
Open circuit.
All the voltage sources short circuit.
Short circuit.
And then
you will only have resistors. Then you find out the effective resistance across those two nodes. And in fact, last term we have done lots of problems where they have two terminals A and B. They find out the effective resistance. We have a whole bunch of series parallel connections, different geometries.
Now that has become more useful.
That has become more useful for them now.
Okay, super.
Correct. And we see that we are using a voltage source and Thevenin resistance.
Correct.
But suppose we had a network with only current sources and resistors, no voltage sources, then there is a slightly different theorem. So if you have, or rather it is a different name, it's a different version of the same theorem.
Okay.
So it turns out that you can represent the same network. So because, so you have some network and you have to N1, N2. Now imagine we had not started with voltage sources. We had started with current sources and resistors. Now when we started with voltage sources and we said that it can be represented with exactly one voltage source in series with one resistance.
Correct.
If we had started with current sources, we have not thought of voltage sources at all, right?
Yeah.
So it turns out that this can be represented across two terminals by one current source and one resistor.
Okay.
But do you think they can be put in parallel, or can they be put in series like earlier?
No, then there will be infinite voltage.
Infinite voltage across the resistor.
When there is no load.
When there is no load, and the current will never change. Whatever load you put, the current will never change. But that is not true for the actual network.
Correct.
So the representation for that would have been like this. A parallel combination of a one current source. We'll call that IN and one resistance Rn. Okay. This theorem is called Norton's theorem or Norton theorem.
Okay.
So this is all named after the scientists who invented this. So Thevenin was one scientist, Norton was another person. But they are both ways to simplify the network. In some cases, current source in parallel with the resistance is easy. In some cases, voltage source in series with the resistance is easy. Turns out, so you imagine I wanted to find out the effective resistance of the network. I have opened all current sources. I have opened the current source IN here. What you are left with is Rn. That has to be the same as
Which is RTH.
So the good thing is there is an equivalence between the two. Okay. So the Thevenin resistance is the same as the Norton resistance, and in fact if you want to find out IN, what we would try to do,
or Thevenin.
Thevenin, in the case of Thevenin we applied open circuit.
Yeah.
Correct?
Correct.
In the case of the Norton current we would short circuit because all of IN would flow through the short circuit.
Yeah.
So clearly the short circuit current has to be equal to IN.
Yeah. Correct.
And we know that this is Thevenin by Thevenin.
Yeah.
So there is a direct relationship between the Thevenin voltage, Thevenin resistance, Norton current.
Yeah. Yes.
Right?
Yes.
So you can go between, you can use either model that you want, depending on what is useful for you.
Super. So if I have a circuit with voltage and current sources.
Yes, you can calculate Norton equivalent or Thevenin equivalent for both. So that is why I said if we had thought about just current sources and resistors, we would have come up with this example. But now that we know networks can have any copy, I think we drew somewhere, it can have, I think we didn't draw it, but in reality, so if your network has all three, so you have current sources and resistors, right? You can use either of the models. So either of the theorems can be used. So I'll show it like this. So you have two nodes, N1, N2. So you can use Thevenin's theorem to replace it with Thevenin in series with Thevenin across N1, N2, and that will be exactly the same as a Norton equivalent across the same N1 and N2.
Okay.
And the relationship will hold. IN is Thevenin by Thevenin, Rn will be Thevenin. Very useful, very powerful technique, which we will keep using again and again in circuit analysis.
So this also means if I have a voltage source and series resistance,
yes,
I can represent as a
Norton
equivalent current source and
always,
and vice versa.
And vice versa. You can, any voltage source in series with a resistance can be converted into a current source in parallel with the resistance and back.
So some kind of source transformation.
Some kind of source transformation, that is right. That's right. Very useful technique, and going forward we will start using these techniques, using Thevenin, Norton, going back and forth to make solving of circuits, analysis of circuits very easy.
So now we have discussed this for DC.
Yes.
But it could be replaced with AC sources.
Absolutely, yes. So now you can have, we'll go to the next level then. So I'll show a bigger network. So I can have DC, I can have DC current sources, I can have AC voltages, AC current sources and resistors. And now what this means is that I can have a Thevenin equivalent. I'll show it like this. Like this. Now this Thevenin voltage will have an AC component and a DC component.
Okay.
So I'll write it like this: Thevenin AC plus Thevenin DC plus Thevenin AC. It will have both. Or you can draw it as a series combination of, Thevenin AC plus Thevenin DC. If
that
you want to
write
write
complicated.
Yes.
Or if I have just AC alone.
Yes. So if you have AC alone, then you can, so suppose
AC voltages and
AC voltages, AC currents
and reactance, resistance.
And resistance, yeah, you're right, you can have inductance, you can have capacitance.
Yeah.
Then what you will have, you will basically have an AC, let's say voltage in, okay, I'm going to draw it like this. Because I don't know whether it is going to be resistance only, capacitance only, inductance only, or a combination of everything. So we had learnt a new term called impedance last time.
Correct.
It's a complex number.
Yeah.
So I'll call it Z Thevenin now.
Okay.
Okay, and this is my
V
V
Thevenin.
Thevenin. And I can also do the same thing for Norton.
Yeah.
So I can have a Norton current in parallel with the Z.
Yeah.
This is also very useful.
Oh, very
We will
nice.
continue to use for AC, DC combination of the two. We will use this.
And this AC, DC together may be a rare combination.
It's a rare combination, correct. It's a rare combination.
Yeah.
I think maybe they will eventually encounter it when they look at electronic circuits in much more detail.
Correct.
Maybe in 2 semesters from now, not right now.
Yeah.
So this is probably the most general case, right? So the most general case would be something like this. So you have combination of AC plus DC and so on. Conceptually you can imagine, but you know, really IN DC plus IN AC, and you will have basically RN, something like this. And probably only DC or only AC is probably what they will see for some time.
So sometimes we use this 1.5 volt battery. You know?
Yes.
If I just like that measure, it gives 1.5.
Correct.
But if I connect a bulb or something or start drawing current,
Yes.
and then if I measure voltage across that load, usually it is lower than 1.5.
That is true. That is true. So what you are saying is that we expected, so I'll show a bulb like this,
Yeah.
right? And so you're saying that
1.5.
you took a 1.5 volt
So
battery.
as per this diagram, bulb should get 1.5.
Should get 1.5.
I don't see that.
You don't see that, right?
So how to account? That means this equivalent circuit is not
It's not
fully
correct. So most likely what you are telling me is when you actually connect the bulb, it's giving out less light than what you expected,
Yeah.
which means less power.
Yeah.
Most likely the current is lesser,
Yes.
right, than what you expect.
So
The
this
only thing I can imagine
Thevenin
is
equivalent
something
and
like
this.
this.
Uh-huh.
You must be having some internal something, you know, we took the case of the resistor divider, no? Where when we actually connected a load, it is not giving you the actual voltage. Most likely
So there must be some internal resistance.
some internal resistance, most likely.
So sometimes when we use this 1.5 volt DC battery, when we measure open circuit voltage, there is 1.5 volt.
Okay.
And if I connect a bulb or something and then measure, it's slightly lower than 1.5.
Yes. It is giving less light than what you expected.
Yeah.
Okay. The only explanation I can imagine, so what you are saying is you connect a 1.5 volt battery
Yeah.
and this is what I expect my circuit to be, right?
Correct.
So I'll show the bulb with a resistance with a circle, but you are getting less light,
Yes.
right? And when you actually measure maybe the current or you can even measure the voltage, no, across the battery.
Correct.
You are saying it is lesser,
Yeah.
right?
So as per this diagram, it should be 1.5.
As per this diagram, it should be 1.5, but you are measuring the V bulb and it is showing less than 1.5.
1.4 or
1.4 or something. Okay.
something.
Well, the only thing that is possible is there must be something else that is dropping that voltage.
Yeah.
Well, it looks like.
So from this Thevenin equivalent circuit, whether we can.
Yes. So in fact, we should draw Thevenin equivalent for the battery, because the battery itself is electrochemically very complicated inside.
Correct.
We don't know what all it contains.
Yeah.
The easiest thing, we don't know what, it's like a network, complicated network, but we can represent it by some, so we can draw it like this, I think.
So we know the open circuit voltage.
We know the open circuit voltage, so that is V Thevenin,
Yeah.
and it has some R Thevenin.
Okay.
Okay. And if you actually connect a bulb, no,
Yeah.
it is no longer 1.5 volts, so this voltage will be lesser.
Oh, so there is some extra voltage drop or some voltage drop in the internal resistance.
In the internal resistance.
Okay.
Okay. And you can probably calculate. So now V Thevenin is clearly 1.5.
Yeah.
You said you didn't connect anything, you just connected only the voltmeter and checked, multimeter and checked.
Yes.
That is showing 1.5.
Yeah.
That is by definition the open circuit voltage.
Correct.
So the Thevenin voltage is 1.5, but the internal resistance we need to find. I don't think you can short circuit it to find the internal resistance.
That may damage the battery.
That may damage the battery. We need to figure out some other easier way. So probably the easiest thing is to connect some known resistance, calculate it and find out, right? So most likely that would be an easier way instead of calculating.
Okay.
For analysis you can analyze, but real measurement you would probably do that.
So this means a simple electrical model of batteries, a voltage source and a
resistance.
series.
Correct. Okay. And a series resistance.
Internal resistance.
Internal resistance. Correct. So what we are saying is that a battery, and a good model for that is something like this. And now we'll call this V. V bat or something.
I think V is also okay.
V is also okay. So we'll just call it V, and we'll call this the internal resistance Rnt to distinguish it from the actual network that we're going to connect outside.
Correct.
Right. So you can see that the Thevenin resistance is Rnt and the open circuit voltage V Thevenin is V, right, for the battery. Correct.
This doesn't represent all aspects of the battery, but it's a better representation.
It's a better representation. Correct. In fact, you can, there is a difference between Rnt when the battery is fully charged versus the battery gets discharged a lot, right? So it is that the actual value of Rnt depends on the state of charge of the battery as well. Correct. Absolutely. So that's an interesting point as well. So maybe next we should go on to solving some examples. Because the best way to learn in circuit analysis is to solve examples.
So we should solve something for Thevenin, Norton, etc.
That's right. AC, DC. We should do all of that. And we should look at using open circuit voltage and the effective resistance. Open circuit voltage divided by short circuit current for that. We should try out all different things for some simple networks to confirm that our understanding is best.
Super.